For over 4,500 years, we've stood before these monuments believing we understood them. We were completely wrong about everything. The precision of these chambers isn't just impressive. It's impossible. The tolerances we're measuring require technology that, according to our timeline of human development, shouldn't have existed for another 4,000 years. We're talking about accuracy levels that modern construction struggles to achieve, carved from blocks weighing 15 tons each, transported from quarries 500 miles away. But here's what makes this truly disturbing: the mathematics encoded in their dimensions predict the speed of light, the Earth's polar radius, and the precession of equinoxes with accuracy that wasn't matched by modern science until the 20th century. These aren't coincidences. These are signatures of technological sophistication that challenges everything we think we know about the progression of human civilization. Tonight, we're diving into the archaeological evidence that suggests at least one ancient civilization achieved levels of advancement that, in many ways, exceed our own. I'm talking about precision that our best modern tools can barely replicate, understanding of physics that we've only recently rediscovered, and engineering solutions that we still can't fully explain. Dr. Christopher Dunn, a precision engineer with decades of experience in aerospace manufacturing, has spent years analyzing the Giza complex using the same measurement techniques applied to modern industrial machinery. His findings: the ancient Egyptians were working with tolerances measured in thousands of inches across, structures spanning acres. That's not just advanced, that's beyond what most modern construction projects achieve today. The implications of what we're about to explore together will fundamentally change how you see human history, technological progress, and our place in the timeline of civilization. Because if this evidence is accurate, we're not the first advanced civilization on this planet. We might not even be the most advanced. For the past 2 centuries, we've operated under a comforting assumption about human progress, that technological advancement follows a neat, linear path from primitive to sophisticated, from simple to complex. We picture our ancestors as gradually discovering fire, then agriculture, then metallurgy, slowly building toward the modern world we inhabit today. This narrative makes intuitive sense. It fits our understanding of how knowledge accumulates over time. But what if this entire framework is wrong? What if the archaeological record contains clear evidence of technological capabilities that do and fit anywhere on our supposed timeline of human development? What if there are ancient sites scattered across the globe that demonstrate engineering precision, mathematical understanding, and construction techniques that rival or exceed our modern capabilities? The evidence isn't hidden in obscure academic journals or fringe theories. It's carved in stone, measured in dimensions, and documented by some of the world's leading archaeologists, engineers, and physicists. The Great Pyramid of Giza incorporates the mathematical constant pi to an accuracy of 0.05%. Puma Punku in Bolivia features interlocking stone blocks with tolerances of 0.01 inches of precision. That requires modern computer-controlled machinery to achieve. Göbekli Tepe in Turkey predates Stonehenge by 6,000 years and displays astronomical alignments that suggest sophisticated understanding of celestial mechanics. Tonight, we're going to examine 3 major revelations that emerge from this evidence. First, that precision machining and advanced mathematics were being employed at least 4,500 years ago, demonstrated through measurement techniques that didn't exist in archaeology until the 1990s. Second, that global navigation and geographic knowledge reached levels that European civilization wouldn't match until the 18th century, evident in maps and monuments that accurately depict landmasses supposedly unknown to ancient peoples. Third, that energy manipulation and acoustic engineering were understood and applied in ways that modern physics is only beginning to appreciate, with structures that demonstrate properties we're still struggling to replicate. These aren't isolated anomalies or measurement errors. They represent systematic evidence of technological sophistication that challenges our fundamental assumptions about the pace and nature of human development. And here's what makes this particularly fascinating: much of this technology wasn't just advanced for its time, it incorporated principles and achieved results that we're still working to understand and replicate today. If you're intrigued by the possibility that human history contains chapters far more sophisticated than we've imagined, subscribe and hit that thumbs up button. And here's something to consider: if an ancient civilization really did achieve advanced technology, what happened to it? Why did such sophisticated knowledge disappear from the historical record? Comment below with your thoughts. I'll pin the most insightful response. The implications extend far beyond academic archaeology or ancient history. If human civilization has achieved advanced technology before, what does that tell us about our current trajectory? What can we learn from civilizations that developed along different technological paths than our own? What warnings might their eventual fate hold for our future? As we explore these questions together, prepare to see familiar monuments and ancient sites through a completely different lens. We're about to examine evidence that suggests human capability, ingenuity, and technological achievement reaches back much further in time than we've ever imagined. The story of advanced ancient civilization isn't just about the past, it's about understanding the true scope of human potential and the cyclical nature of technological development. Now let us begin by examining the mathematical precision hidden in plain sight within humanity's most enduring monuments. Hidden precision. When you look at the Great Pyramid of Giza, what do you see? Most people see ancient stones, impressive scale, and a testament to pharaonic power. What you're actually seeing is the most precisely constructed building in human history, incorporating mathematical constants and geometric relationships that would be formally discovered by modern mathematics for thousands of years. The base perimeter of the Great Pyramid, when divided by its height, produces the mathematical constant pi accurate to 0.05%. Let that sink in for a moment. Pi, the relationship between a circle's circumference and diameter, was supposedly first calculated by the Greeks around 250 BC, more than 2,000 years after the pyramid's construction. Yet there it is, encoded in stone blocks weighing 2.5 tons each, positioned with tolerances measured in millimeters across a base spanning 13 acres. This isn't the kind of precision that emerges from trial and error or lucky accidents. Dr. Christopher Dunn, who spent decades as a precision engineer in the aerospace industry, has applied modern measurement techniques to analyze the pyramid's construction. Using coordinate measuring machines and laser interferometry, the same tools used to manufacture jet engines, he has documented construction accuracies that rival modern industrial standards. The southeast corner of the pyramid's base differs in height from the northwest corner by less than half an inch across a distance of 755 feet. That's a construction tolerance of 0.0006%. To put this in perspective, modern construction projects typically work with tolerances between 0.1% and 1%. The Pentagon, built with 20th century technology and precision tools, has foundation tolerances 10 times greater than what the ancient Egyptians achieved with supposedly primitive technology. The pyramid's base is leveled to within 2.1 centimeters across its entire area, a feat that requires not just advanced mathematical understanding, but precision instruments for measurement and construction. But the mathematical encoding goes far deeper than pi. The pyramid's dimensions also incorporate the golden ratio phi, the mathematical relationship that appears throughout natural systems and optimal design. The height of the pyramid relates to its base through phi with 99.5% accuracy. The chambers within the pyramid, the King's Chamber, Queen's Chamber, and Grand Gallery, are positioned using geometric relationships based on phi and other mathematical constants. Consider the engineering challenge this represents. You're working with limestone blocks quarried 500 miles away, granite elements transported from Aswan 600 miles to the south, and a construction timeline estimated at 20 years. Every block must be cut, transported, positioned, and fitted with tolerances that modern construction rarely achieves. The internal chambers must align perfectly with external dimensions while maintaining structural integrity capable of supporting 5.9 million tons of stone. The internal passageways of the pyramid are oriented to celestial alignments with precision that requires sophisticated astronomical knowledge. The descending passage points to the pole star as it appeared in 2450 BC, not as it appears today, but accounting for the precession of equinoxes over a 25,920-year cycle. This level of astronomical calculation was matched in European astronomy until Copernicus and Kepler developed their mathematical models of celestial mechanics in the 16th and 17th centuries. Recent discoveries using cosmic ray imaging have revealed additional chambers within the pyramid that weren't known to exist until 2017. These chambers maintain the same geometric relationships and mathematical proportions as the known internal structure, 45 centuries after construction. We're still discovering how sophisticated this building really is. Each new measurement technique reveals additional layers of precision and mathematical encoding that seem to exceed what we initially measured. The ancient Egyptians achieved this level of precision across multiple pyramid sites. The pyramids at Giza aren't isolated examples. They represent the culmination of sophisticated mathematical and engineering knowledge applied consistently across generations of construction projects. The earlier pyramids at Saqqara and Meidum show progressive development of the techniques that would reach their peak in the Giza complex. What makes this precision particularly remarkable is that it wasn't just applied to external dimensions but extends to internal details that would be visible or measurable to future visitors. The sarcophagus in the king's chamber is carved from a single piece of granite with internal corners that form perfect right angles accurate to within 0.05 degrees. The walls of the chamber itself are flat and parallel to tolerances of 0.0 to 5 centimeters, a precision that requires measurement tools we assume didn't exist in ancient Egypt. The mathematical knowledge demonstrated in these structures suggests understanding of advanced geometric principles, including the relationships between two-dimensional and three-dimensional shapes, the properties of irrational numbers like pi and phi, and the mathematical description of astronomical cycles. This wasn't primitive building scaled up through brute force, this was sophisticated engineering applied with mathematical precision. As we examine other ancient sites around the world, this pattern of mathematical encoding and precision construction appears repeatedly. The ancient Egyptians weren't alone in achieving levels of technological sophistication that challenge our assumptions about the capabilities of early civilizations. But if such precision was possible for 1,500 years ago, why do we see it as remarkable today? What happened to the knowledge and techniques that made such achievements routine rather than mysterious? Impossible engineering 6,000 miles from Giza, on a windswept plateau 12,500 feet above sea level in Bolivia, sits Puma Punku, a site that pushes the boundaries of what we consider possible in ancient construction even further than the pyramids. Here, massive blocks of andesite and sandstone weighing up to 450 tons have been cut, shaped, and fitted together with precision that requires computer-controlled machinery to achieve. The blocks at Puma Punku aren't just precisely cut, they were designed with complex interlocking geometries that could only be planned using three-dimensional modeling. These aren't simple rectangular blocks stacked on top of each other. They feature precise channels, grooves, and connecting elements that fit together like components of a massive mechanical system. The tolerances between connecting surfaces are measured in thousands of inches. Modern stone cutting using diamond-tip tools struggles to match this level of precision. Dr. Brian Forster, who has conducted extensive research at Puma Punku using precision measurement tools, has documented construction techniques that don't align with any known ancient technology. The surfaces of these blocks are flat and parallel to tolerances of 0.01 inches across spans of several feet. The corners form perfect right angles accurate to within 0.05 degrees. The connecting elements are cut with internal geometries that require three-dimensional planning and precision machinery to execute. But here's what makes Puma Punku truly mystifying: andesite, the primary stone used in construction, rates between 6 and 7 on the Mohs hardness scale. That makes it harder than steel and nearly as hard as quartz. Cutting and shaping andesite with the precision demonstrated at Puma Punku requires diamond-tip tools operating under computer control. The ancient peoples of Bolivia supposedly had only copper, bronze, and stone tools available, materials that would be worn away by andesite rather than cutting it. The construction also demonstrates advanced understanding of load distribution and structural engineering. The massive blocks are positioned to distribute weight evenly across their supporting surfaces. using principles of structural load management that weren't formally developed in engineering until the 9th century. The connecting systems between blocks create self-reinforcing structures that become more stable under load rather than less stable. Even more puzzling is the evidence of machining operations. Many blocks show perfectly flat surfaces that could only be created using machinery capable of maintaining consistent cutting depth across large areas. Some surfaces display parallel ridges consistent with mechanical cutting or grinding operations. Others show evidence of drilling operations that created perfectly round holes with smooth internal walls, again operations that require precision machinery to achieve. The logistics of construction present additional mysteries. The nearest source of andesite is 10 miles away across difficult terrain. Moving 450-ton blocks across this distance using primitive technology would require transportation systems that don't appear in the archaeological record. The blocks would need to be lifted and positioned with precision that requires sophisticated lifting equipment, yet no evidence exists of the massive infrastructure such operations would require. Recent analysis using ground-penetrating radar has revealed that Puma Punku sits atop an extensive underground complex of chambers and tunnels that extend far beyond the visible surface structures. This underground network shows the same precision construction techniques as the surface blocks, suggesting that the sophisticated engineering capabilities were applied to much larger projects than what remains visible today. The age of Puma Punku presents another challenge to conventional understanding. Carbon dating of organic materials found in the construction dates portions of the site to at least 15,000 years ago, placing it among the oldest stone construction on Earth. This predates the development of agriculture, written language, and metallurgy by thousands of years according to standard archaeological timelines. But the precision engineering at Puma Punku isn't unique in the archaeological record. Similar techniques appear at sites across the globe that supposedly had no contact with each other. In Peru, the stone walls at Sacsayhuaman feature blocks weighing up to 200 tons fitted together with precision that won't allow a knife blade to slip between them. In Egypt, the granite boxes at the Serapeum of Saqqara are carved from single pieces of stone with internal dimensions accurate to within 0.001 inches. These examples represent a systematic pattern of precision engineering that appears across multiple continents and time periods. The techniques involved require not just advanced tools, but sophisticated understanding of geometry, materials science, and structural engineering. The level of planning and coordination needed to execute such projects suggests civilizations with advanced technical knowledge and organizational capabilities. What's particularly striking is that in many cases, the precision achieved in ancient construction exceeds what we routinely accomplish in modern projects. The Egyptian pyramid builders achieved construction tolerances that surpass most contemporary architecture. The stone cutting at Puma Punku requires precision that few modern stoneworking operations can match. These weren't primitive peoples stumbling toward technological development. These were civilizations that had mastered sophisticated engineering techniques. The evidence suggests that advanced engineering capabilities have existed far longer than our current models of technological development predict. The question is whether ancient peoples could achieve such precision, and the evidence clearly demonstrates that they did. The question is how they developed these capabilities and what happened to the knowledge and technology that made such achievements possible. But precision engineering represents only one aspect of ancient technological sophistication. The mathematical understanding required to plan such construction projects reveals knowledge that extends far beyond practical building techniques into realms of advanced science and mathematics. Mathematical mastery. The mathematical knowledge encoded in ancient monuments goes far beyond what would be needed for practical construction. These structures incorporate advanced mathematical concepts that would be formally developed by academic mathematics for thousands of years, suggesting understanding of numerical relationships and geometric principles that rival or exceed modern mathematical education. The Great Pyramid provides the most extensively documented example of ancient mathematical sophistication, beyond the encoding of pi and phi. The structure incorporates precise relationships to Earth's dimensional properties that require Advanced geographic and astronomical knowledge. The pyramid's height, when multiplied by 43,200, equals the polar radius of Earth to an accuracy of 99.8%. The base perimeter, when multiplied by the same number, equals Earth's circumference at the equator with 99.9% accuracy. These relationships aren't coincidences. The number 43,200 itself represents advanced understanding of celestial cycles and mathematical scaling. The mathematical encoding extends to sophisticated understanding of irrational numbers and their practical application. The King's Chamber within the Great Pyramid has dimensions based on Pythagorean triangles with ratios of 3 to 4 to 5 and 5 hours 12 minutes and 13 seconds, but these aren't simple applications of the Pythagorean theorem. The chamber incorporates these ratios into a three-dimensional space where multiple mathematical relationships operate simultaneously. The internal geometry creates what mathematicians call a resonance chamber, a space whose dimensional relationships produce specific harmonic frequencies when excited by sound or vibration. The mathematical calculations required to design such a space require understanding of acoustic principles, harmonic mathematics, and three-dimensional geometry that wasn't formally developed until the modern era. Yet the chamber demonstrates these principles applied with precision that produces measurable acoustic effects. Dr. John Anthony West, who has studied the mathematical properties of Egyptian monuments for decades, has identified systematic use of sacred geometry throughout Egyptian construction. This isn't random application of mathematical concepts, but consistent use of specific proportions and relationships that appear across multiple sites and time periods. The same mathematical ratios that govern the Great Pyramid appear in temples throughout Egypt, suggesting standardized mathematical knowledge passed down through generations of builders. But Egyptian mathematical sophistication wasn't isolated to monument construction. The Rind papyrus, dating to 1650 BC, demonstrates mathematical techniques including fractions, geometric progression, and calculation methods for areas and volumes of complex shapes. The ancient Egyptians were working with mathematical concepts that included early versions of calculus and trigonometry, mathematical tools that European scholars wouldn't develop. Until the 17th century, mathematical sophistication appears in other ancient cultures with equal complexity. The Mayan calendar system incorporates calculations based on astronomical cycles, extending millions of years into the past and future. Their mathematical system used the concept of zero independently of its development in India and included sophisticated understanding of astronomical periods accurate to within seconds per year. Over centuries of observation, the Mayan calendar demonstrates knowledge of celestial mechanics that requires mathematical modeling of planetary motions, lunar cycles, and stellar positions across extended time periods. The long count calendar, which tracks time in cycles of 144,000 days, shows understanding of mathematical scaling and cyclic calculation that rivals modern astronomical computation. Their predictions of eclipses, planetary conjunctions, and seasonal variations were accurate across centuries of observation. Ancient Mesopotamian mathematics included sophisticated number systems and geometric techniques. Babylonian mathematicians were working with quadratic equations, exponential functions, and geometric series 3,000 years before these concepts were formally developed in European mathematics. They calculated square roots and cube roots to multiple decimal places using iterative methods that weren't rediscovered in European mathematics until the Renaissance. The mathematical knowledge demonstrated in ancient construction projects required not just theoretical understanding, but practical application of mathematical concepts to real-world engineering problems. Calculating the precise positioning of massive stone blocks requires trigonometry and geometric modeling. Designing internal chambers with specific acoustic properties requires mathematical understanding of wave mechanics and harmonic relationships. Evidence suggests that ancient mathematical knowledge included concepts that modern mathematics has only recently begun to appreciate. The golden ratio phi appears throughout ancient architecture and art in ways that suggest understanding of its mathematical properties in natural systems, growth patterns, and optimal design principles. This knowledge was being applied practically thousands of years before modern mathematics formally described the mathematical principles involved. Ancient astronomical calculations demonstrate mathematical sophistication that required systematic observation, data collection, and mathematical modeling across centuries. The precision of ancient eclipse predictions, calendar calculations, and astronomical alignments requires mathematical techniques capable of modeling complex celestial mechanics. These calculations were being performed accurately when European astronomy still relied on basic geometric models that couldn't account for observed astronomical phenomena. The consistency of mathematical knowledge across different ancient cultures suggests educational systems capable of preserving and transmitting sophisticated mathematical concepts across generations. This was primitive mathematics gradually developing toward sophistication. This was advanced mathematical knowledge systematically applied to practical problems including construction, astronomy, and engineering. The mathematical capabilities demonstrated in ancient monuments and documents exceed what most modern educational systems teach at undergraduate levels. These civilizations were working with mathematical concepts that required advanced understanding of number theory, geometry, and applied mathematics. The precision of their calculations and the consistency of their applications suggest mathematical knowledge that was both theoretically sophisticated and practically effective. If ancient peoples possessed such advanced mathematical knowledge, what other areas of science and technology might they have developed beyond what the archaeological record has yet revealed? The mathematical sophistication evident in their monuments suggests civilizations capable of scientific investigation and technological development across multiple domains. But mathematical knowledge represents only the foundation for the astronomical observations and geographic knowledge that ancient civilizations demonstrated with remarkable accuracy. Celestial knowledge. The astronomical knowledge demonstrated by ancient civilizations extends far beyond simple observation of obvious celestial patterns. These cultures were tracking celestial movements, predicting astronomical events, and incorporating cosmic cycles into their monuments with accuracy that required sophisticated mathematical modeling and systematic observation across centuries. The ancient Egyptians aligned their pyramids to stellar positions with precision that requires detailed knowledge of celestial mechanics. But they weren't just observing the night sky as it appeared during their lifetimes. They were calculating stellar positions, accounting for the precession of equinoxes, the slow wobble of Earth's axis that causes star positions to shift over cycles of 25,920 years. The Great Pyramid's passages point to stellar positions as they appeared in 2450 BC, correcting for precessional changes that wouldn't be formally understood in Western astronomy until the work of Hipparchus around 190 BC. This level of astronomical calculation requires understanding that Earth's rotational axis isn't fixed, that stellar positions change over long time periods, and that these changes follow predictable mathematical patterns. Ancient Egyptian astronomers were performing calculations that required knowledge of spherical trigonometry and long-term stellar mechanics. They were modeling celestial movements across timescales spanning thousands of years. The precision of these calculations becomes even more remarkable when we examine the broader pattern of astronomical alignments in Egyptian monuments. The pyramids at Giza are positioned to mirror the constellation Orion as it appeared around 10,500 BC, not during the time of their construction, but during a specific period in the distant past when Orion reached its lowest point in its precessional cycle. This alignment requires astronomical calculations extending back over 7,000 years before the pyramids were built. Dr. Robert Bauval, whose research into Egyptian astronomical alignments has revealed systematic correlation between pyramid positions and stellar configurations, has documented how Egyptian monuments incorporate multiple time periods of astronomical significance. The Giza complex reflects stellar positions from both the distant past and projected future positions, suggesting astronomical knowledge that could model celestial mechanics across multiple complete precessional cycles. But Egyptian astronomical sophistication wasn't limited to stellar observations. They tracked planetary movements with accuracy that required mathematical modeling of orbital mechanics. Their calendar system incorporated both solar and stellar observations, maintaining accuracy across centuries without the accumulating errors that plagued later calendar systems. They predicted eclipses, calculated seasonal variations, and tracked lunar cycles with precision that required systematic observation and mathematical calculation. Ancient Mayan astronomy demonstrates even more sophisticated mathematical modeling of celestial mechanics. The Mayan calendar system tracks multiple astronomical cycles simultaneously, including solar years, lunar months, Venus synodic periods, and Mars orbital cycles. Their calculations of these periods were accurate to within seconds per year, maintained across centuries of observation. This level of precision requires mathematical techniques capable of modeling complex orbital relationships and predicting astronomical events decades in advance. The Dresden Codex, a Mayan astronomical text, contains tables for calculating eclipse patterns, planetary positions, and calendar correlations extending thousands of years into both past and future. These calculations incorporate correction factors for the small discrepancies between observed astronomical periods and their mathematical models, adjustments that require sophisticated understanding of observational error and mathematical precision. Mayan astronomers calculated the length of the solar year as 365.242 days, accurate to within 0.002 days compared to modern measurements. They calculated Venus's synodic period as 583.92 days, compared to the modern measurement of 583.93 days. These weren't rough approximations based on casual observation. These were precise calculations based on systematic astronomical observation and mathematical modeling maintained across generations of astronomer priests. Ancient Mesopotamian astronomy demonstrates similar mathematical sophistication applied to celestial observation. Babylonian astronomers developed mathematical models for predicting planetary positions that used numerical techniques including interpolation, extrapolation, and iterative calculation methods. Their astronomical texts contain detailed tables for calculating planetary positions, eclipse predictions, and calendar correlations. The Babylonian astronomical text MUL API contains star catalogs, constellation maps, and mathematical tables for calculating celestial positions. Their observations included accurate measurements of the length of seasons, the timing of equinoxes and solstices, and the periods of planetary movements. They developed mathematical models that could predict astronomical events with accuracy that wouldn't be matched in European astronomy until the work of Kepler and Newton. What makes this ancient astronomical knowledge particularly remarkable is that much of it was developed using naked-eye observation without telescopic instruments. These civilizations were tracking planetary movements, stellar positions, and celestial cycles using mathematical techniques that required precise observation, systematic data collection, and sophisticated calculation methods. They were performing astronomical mathematics that modern astronomy accomplishes using computer modeling and telescope-assisted observation. The consistency of astronomical knowledge across different ancient cultures suggests systematic development of observational techniques and mathematical methods. Egyptian, Mayan, and Mesopotamian astronomical systems show similar levels of sophistication and accuracy. Despite supposedly developing independently, this suggests either cultural exchange between distant civilizations or independent development of similar advanced astronomical capabilities. Ancient monuments incorporate astronomical alignments that require not just observational astronomy, but engineering capabilities to implement astronomical calculations in stone construction. The precise orientation of passages, chambers, and structural elements to specific stellar positions requires mathematical techniques for translating astronomical coordinates into architectural measurements. This represents the practical application of advanced astronomical knowledge to construction projects spanning decades. Recent analysis using modern astronomical software has revealed that many ancient monuments incorporate astronomical alignments that weren't visible to the naked eye from their geographic positions. Some alignments point to celestial positions that would have been below the horizon during the time periods when the monuments were supposedly constructed. This suggests either much older construction dates than currently accepted, or astronomical knowledge that could calculate stellar positions without direct observation. The astronomical capabilities demonstrated by ancient civilizations include mathematical techniques, observational precision, and theoretical understanding that rival modern astronomical education. These weren't primitive stargazers gradually learning to track obvious celestial patterns. These were sophisticated astronomical observatories conducting systematic investigation of celestial mechanics using advanced mathematical techniques. If ancient civilizations possessed such sophisticated astronomical knowledge, what does this suggest about their understanding of physics, mathematics, and their place in the cosmos? The precision of their observations and calculations indicates scientific investigation that extended far beyond practical applications into theoretical understanding of natural phenomena. But astronomical knowledge represents only one dimension of the global awareness that ancient civilizations demonstrated through their geographic knowledge and navigation capabilities. Global awareness. The geographic knowledge demonstrated by ancient civilizations extends far beyond what should have been possible given the supposed limitations of their transportation and communication systems. Ancient maps, navigation techniques, and geographic references reveal awareness of global geography that was matched by European exploration until the 18th century. The Piri-Reis map of 1513 provides one of the most compelling examples of ancient geographic knowledge. This Turkish admiral's map shows the coastlines of South America and Antarctica with remarkable accuracy, including geographic features that weren't officially discovered by European exploration until centuries later. But here's what makes this map truly mystifying. Piri-Reis stated in his notes that he compiled the map using ancient source materials, including maps that dated back to the time of Alexander the Great. The Antarctic coastline shown on the Piri-Reis map depicts the continent as it would appear without its ice sheet, geographic features that have been covered by ice for at least 6,000 years. Modern mapping of Antarctica as sub-ice topography using ground-penetrating radar and seismic surveys confirms that the map accurately shows mountain ranges, coastlines, and geographic features that are currently buried under miles of ice. Charles Hapgood, who conducted extensive research into ancient cartography, documented how the Piri-Reis map demonstrates advanced understanding of longitude calculation and spherical projection technique. Quest. The map uses mathematical methods for projecting spherical Earth onto flat surfaces that would be formally developed in European cartography until the 16th century. The accuracy of longitude calculations requires precise timekeeping and mathematical techniques that supposedly weren't available to ancient navigators. But the Piri-Reis map isn't an isolated example of advanced ancient cartography. The Orontes Phineas map of 1532 shows Antarctica as an ice-free continent with rivers, mountains, and coastlines. The Mercator map of 1569 depicts Arctic regions with geographic features that wouldn't be officially discovered until 20th century polar exploration. These maps consistently show geographic knowledge that extends far beyond what contemporary exploration had achieved. Ancient navigation capabilities provide additional evidence of global geographic awareness. Polynesian navigators were crossing thousands of miles of open ocean using techniques that required precise understanding of celestial navigation, ocean current patterns, and geographic relationships between distant island groups. They developed navigation methods that could maintain accuracy across voyages spanning weeks or months without sight of land. The mathematical precision of Polynesian navigation requires understanding of spherical trigonometry, celestial mechanics, and mathematical techniques for calculating position using stellar observations. Their navigation methods account for seasonal changes in stellar positions, variations in ocean current patterns, and the mathematical relationships between celestial coordinates and geographic positions. This represents sophisticated application of mathematical knowledge to practical navigation problems. Recent research has revealed that ancient navigators possessed detailed knowledge of global wind patterns, ocean current systems, and seasonal weather variations. They developed navigation techniques that incorporated understanding of natural phenomena, including magnetic declination, atmospheric refraction, and the mathematical relationships between celestial observations and geographic coordinates. Evidence suggests that ancient civilizations maintained regular contact across distances that supposedly exceeded their transportation capabilities. Cultural similarities, technological techniques, and architectural styles appear across continents that, according to conventional timelines, had no contact with each other. The spread of specific agricultural techniques, mathematical concepts, and astronomical knowledge suggests communication networks that span global distances. The presence of cocaine and tobacco residues in Egyptian mummies provides chemical evidence of contact between ancient Egypt and the Americas. These plant materials don't grow naturally in Africa or the Middle East, yet they appear in mummy preparations dating to 1000 BC or earlier. This suggests either long-distance trade networks or transportation capabilities that could cross ocean distances regularly enough to maintain supply chains for exotic materials. Ancient mining operations demonstrate geographic knowledge that extends across multiple continents. Copper mining sites in Michigan's Upper Peninsula show evidence of ancient extraction activities that removed millions of pounds of copper ore. The scale of these operations suggests industrial level mining that required transportation systems capable of moving massive quantities of raw materials across continental distances. The mathematical techniques required for global navigation include sophisticated understanding of Earth's spherical geometry, the mathematical relationships between celestial coordinates and terrestrial positions, and calculation methods for determining position and direction across long distances. Ancient navigators were performing calculations that required mathematical knowledge equivalent to modern navigation techniques. Geographic knowledge encoded in ancient monuments demonstrates awareness of Earth's dimensional properties that requires global-scale geographic investigation. The mathematical relationships between pyramid dimensions and Earth's polar radius and circumference suggest measurements that could only be obtained through systematic geographic survey. Across continental distances, ancient astronomers tracked stellar positions and celestial cycles that required observation posts distributed across multiple geographic locations. The accuracy of their astronomical calculations suggests coordinated observation networks that could maintain systematic data collection across continents. This level of coordination requires communication systems and organizational capabilities that imply sophisticated technological infrastructure. The distribution of megalithic construction techniques across multiple continents suggests either independent development of similar advanced technologies or cultural exchange that could transmit sophisticated engineering knowledge across global distances. The consistency of mathematical principles, construction techniques, and astronomical alignments across geographically separated sites indicate systematic sharing of advanced technical knowledge. Evidence of ancient global awareness challenges conventional understanding of technological development and cultural exchange in early civilizations. The geographic knowledge, navigation capabilities, and international connections demonstrated by ancient peoples suggest technological and organizational capabilities that rival or exceed many aspects of modern global communication and transportation systems. Recent discoveries using satellite archaeology and ground-penetrating radar have revealed extensive ancient transportation networks including roads, canals, and harbor facilities that connected distant regions through systematic infrastructure development. These networks required engineering capabilities, organizational systems, and technological resources that suggest civilizations with advanced planning and construction capabilities. If ancient civilizations possess global geographic awareness and navigation capabilities, what other aspects of their technological development might have achieved levels of sophistication that we are only beginning to appreciate? The evidence suggests systematic investigation of natural phenomena and practical application of advanced knowledge across multiple domains of science and technology. But global awareness represents only one aspect of the technological capabilities that ancient civilizations demonstrated through their sophisticated engineering solutions and practical applications of advanced scientific knowledge. Energy mastery. The most intriguing aspect of ancient technological sophistication may be their apparent understanding and manipulation of energy systems that modern physics is only beginning to appreciate. ancient sites around the world demonstrate properties related to acoustic resonance, electromagnetic fields, and geological energy that suggest systematic knowledge of natural forces we're still working to understand. The Great Pyramid of Giza functions as a sophisticated acoustic resonance chamber that amplifies and focuses sound waves in ways that require advanced understanding of harmonic mathematics and acoustic engineering. When sound waves are introduced into the king's chamber, the room produces resonance effects at specific frequencies that correspond to mathematical relationships encoded in the chamber's dimensions. This is an accidental of the mathematical ratios that govern the chamber as proportions are specifically designed to create these acoustic effects. Dr. John Stuart Reid, who has conducted extensive acoustic research within the Great Pyramid using modern sound analysis equipment, has documented how the pyramid's internal chambers function as a complex acoustic system. The Grand Gallery acts as a resonating chamber that amplifies specific frequencies. The King's Chamber focuses acoustic energy at precise mathematical harmonics, and the overall structure creates acoustic effects that can be measured throughout the internal passages. The acoustic properties aren't limited to simple resonance. The pyramid demonstrates sophisticated understanding of acoustic focusing, harmonic amplification, and sound wave manipulation that requires mathematical modeling of wave mechanics. The chamber dimensions create acoustic effects that include standing wave patterns, harmonic overtones, and acoustic focusing that concentrates sound energy at specific points within the structure. But acoustic engineering represents only one aspect of the energy systems demonstrated in ancient construction. Recent research using sensitive electromagnetic field detectors has revealed that many ancient megalithic sites generate measurable electromagnetic anomalies that correlate with geological features, including underground water sources, mineral deposits, and geological fault systems. Stonehenge sits atop a complex network of underground water channels and geological formations that create natural electromagnetic field variations. The placement of the stone circle precisely correlates with the intersection points of underground water systems and geological features that produce measurable electromagnetic effects. This suggests that ancient builders possessed knowledge of subsurface geology and electromagnetic field detection that could identify optimal locations for their constructions. Similar electromagnetic anomalies appear at megalithic sites across Europe, including Avebury, Carnac, and Newgrange. These sites consistently demonstrate correlation between stone placement and underground geological features that produce electromagnetic field variations. The precision of site selection suggests systematic knowledge of geological surveying techniques and electromagnetic field detection methods. Recent analysis using ground-penetrating radar and electromagnetic field mapping has revealed that many ancient sites incorporate sophisticated understanding of geological engineering. The Giza Pyramid Complex sits atop natural geological formations that create underground acoustic chambers and electromagnetic field concentrations. The pyramid construction appears to enhance and focus these natural geological effects rather than simply sitting passively on the landscape. Ancient temple complexes in India demonstrate sophisticated understanding of acoustic design and energy manipulation. The temples at Chidambaram and Thanjavur incorporate architectural features that create specific acoustic effects including sound amplification, acoustic focusing, and harmonic resonance. The mathematical precision required to design such effects indicates advanced understanding of acoustic engineering principles. The acoustic properties of these temples include sophisticated effects that require mathematical modeling of sound wave behavior in complex architectural spaces. The temples create acoustic environments that amplify and focus sound at specific frequencies, produce harmonic overtones that enhance musical performance, and generate acoustic effects that can be precisely controlled through architectural design. Energy manipulation capabilities appear in other aspects of ancient technology, including crystal cutting and shaping techniques that require understanding of crystal structure and resonance properties. Ancient sites in South America demonstrate precision cutting and shaping of quartz crystals using techniques that require knowledge of crystal resonance frequencies and mechanical properties. The precision achieved in ancient crystal working suggests understanding of materials science. Principles including crystal structure, mechanical properties, and resonance characteristics. Ancient craftsmen were working with crystals in ways that required knowledge of optimal cutting angles, resonance frequencies, and structural engineering principles applied to crystalline materials. Evidence suggests that ancient civilizations understood and systematically applied natural energy phenomena that modern science is still investigating. The correlation between ancient site locations and geological energy phenomena indicates systematic knowledge of Earth's natural energy systems and practical techniques for detecting and utilizing these phenomena. Recent research into ancient mining operations has revealed sophisticated understanding of geological surveying and resource location techniques. Ancient miners were locating underground ore deposits, water sources, and geological formations using methods that required knowledge of geological principles and systematic surveying techniques. The precision of ancient resource location suggests understanding of geological science principles including geological surveying, subsurface feature detection, and resource assessment techniques. Ancient civilizations were conducting geological investigation and resource development using systematic methods that required advanced understanding of Earth's geological systems. Ancient astronomical observatories demonstrate understanding of natural energy cycles and their correlation with celestial movements. Many sites incorporate features that respond to seasonal changes in solar energy, lunar cycles, and stellar positions in ways that suggest systematic knowledge of natural energy variations and their relationship to astronomical phenomena. The integration of astronomical observation with energy system understanding suggests sophisticated investigation of natural phenomena and their practical applications. Ancient civilizations were studying the relationships between celestial cycles, terrestrial energy systems, and natural phenomena using systematic observation and mathematical analysis. Energy system knowledge appears throughout ancient technology including metallurgy, construction techniques, and precision manufacturing. Ancient metal workers achieved results that require understanding of thermodynamics, materials science, and precision manufacturing techniques. Their metallurgical achievements demonstrate sophisticated understanding of energy manipulation applied to materials processing. The evidence suggests that ancient civilizations possessed systematic knowledge of natural energy phenomena and practical techniques for utilizing these systems in construction, manufacturing, and technological applications. Their understanding of acoustic engineering, electromagnetic field detection, and geological energy systems represents sophisticated investigation of natural phenomena that modern science is still working to fully understand. If ancient peoples possess such sophisticated understanding of natural energy systems, what other aspects of physics and natural science might they have investigated and applied to practical technological problems? The evidence suggests systematic scientific investigation that extended across multiple domains of natural phenomena. But energy manipulation represents only one dimension of the technological capabilities that ancient civilizations demonstrated through their advanced manufacturing techniques and precision engineering. Manufacturing mastery. The manufacturing capabilities demonstrated in ancient artifacts reveal technological sophistication that rivals and sometimes exceeds modern industrial production. Ancient craftsmen were achieving levels of precision, material manipulation, and manufacturing complexity that require advanced understanding of materials science, precision engineering, and sophisticated manufacturing techniques. The granite vases found in Egyptian tombs provide compelling evidence of ancient precision manufacturing that pushes the boundaries of what we consider possible with primitive tools. These vases are carved from solid granite, one of the hardest materials available, yet demonstrate wall thicknesses of less than a quarter-inch, internal geometries with complex curves and chambers, and surface finishes that require precision grinding and polishing techniques. The internal chambers of these granite vases include features that can only be created using precision machining techniques. Some vases have internal chambers with curves and angles that require three-dimensional cutting. Operations impossible to achieve with hand tools, the smooth internal surfaces and consistent wall thicknesses require precision control that matches modern computer-controlled machining operations. Christopher Dunn, whose background in aerospace precision manufacturing provides expertise in evaluating ancient machining evidence, has documented manufacturing techniques in Egyptian artifacts that require industrial-level precision and control. The granite boxes in the Serapeum of Saqqara demonstrate machining operations including precision drilling, internal corner forming, and surface finishing that require sophisticated manufacturing equipment. The Serapeum boxes are carved from single pieces of granite weighing up to 100 tons each, with internal dimensions accurate to within 0.001 inches. The internal corners form perfect right angles, the walls are parallel and flat to extremely tight tolerances, and the surface finishes indicate precision grinding operations. These manufacturing achievements require not just advanced tools, but sophisticated understanding of materials science, precision measurement, and quality control. Evidence of ancient precision drilling appears in artifacts across multiple cultures and time periods. Core holes in Egyptian granite demonstrate drill rates, feed patterns, and cutting characteristics that require industrial diamond drilling equipment to replicate. The drilling operations show consistent feed rates, uniform cutting patterns, and precision that matches modern diamond core drilling techniques. The drilling evidence includes features that are characteristic of modern industrial operations: consistent spiral feed marks, uniform cutting rates, and drill core removal techniques that require sophisticated drilling equipment. Ancient drillers were achieving results that require understanding of drilling mechanics, cutting tool materials, and precision manufacturing techniques. Ancient metalworking demonstrates sophisticated understanding of metallurgy, alloy composition, and precision casting techniques. The Damascus steel produced in ancient Syria and India achieved material properties that modern metallurgy struggles to replicate. These steels demonstrate understanding of carbon distribution, heat treatment, and alloy design that requires advanced materials science knowledge. The manufacturing techniques used to create Damascus steel include precision temperature control, systematic heat treatment cycles, and forging operations that require sophisticated understanding of materials science. The resulting material properties include hardness, flexibility, and edge retention characteristics that represent optimal balance of material properties through advanced metallurgical techniques. Ancient bronze working achieved precision casting and alloy composition that indicates sophisticated understanding of metallurgical chemistry and manufacturing processes. Ancient bronze artifacts demonstrate alloy compositions precisely controlled for specific applications, casting techniques that achieve complex geometries, and finishing operations that require precision manufacturing equipment. The lost wax casting techniques used in ancient bronze production require sophisticated understanding of thermal dynamics, mold design, and precision manufacturing processes. Ancient craftsmen were producing cast bronze objects with internal features, complex geometries, and surface finishes that require advanced casting technology and materials science knowledge. Evidence of ancient precision grinding and polishing appears in stone artifacts that demonstrate surface finishes requiring industrial-grade equipment. Ancient mirror surfaces carved from obsidian and other materials achieve optical quality finishes that require precision grinding techniques and sophisticated understanding of optical principles. The optical properties of ancient mirrors include surface accuracy, reflectivity, and distortion characteristics that match modern precision optical manufacturing. Creating such optical surfaces requires understanding of optical principles, precision grinding techniques, and quality control methods that represent advanced manufacturing capabilities. Ancient textile production demonstrates sophisticated understanding of materials science, precision manufacturing, and systematic production techniques. Ancient textiles include fibers processed to precise specifications, weaving patterns that require mathematical precision, and finishing techniques that indicate advanced manufacturing knowledge. The complexity of ancient textile production includes fiber processing techniques, dyeing operations that require sophisticated chemistry, and weaving operations that require precision manufacturing equipment. Ancient textile producers were achieving results that require systematic understanding of materials science and precision. Manufacturing techniques. Ancient ceramic production achieved material properties and manufacturing precision that indicate sophisticated understanding of ceramic chemistry and thermal processing. Ancient ceramics demonstrate controlled composition, precision forming, and thermal treatment that require advanced understanding of materials science and manufacturing processes. The ceramic manufacturing techniques include precise temperature control, controlled atmosphere processing, and systematic quality control that represent advanced manufacturing capabilities. Ancient ceramic producers were achieving material properties and manufacturing precision that require sophisticated understanding of ceramic science and thermal processing techniques. Manufacturing evidence appears in the systematic production of precision tools, weapons, and implements that demonstrate standardization, quality control, and precision manufacturing across multiple production sites. Ancient manufacturers were maintaining consistent quality standards, precise specifications, and systematic production techniques across extended geographic areas. The standardization of ancient manufacturing suggests organized production systems, systematic quality control, and precision manufacturing techniques that require advanced understanding of materials science, precision measurement, and systematic manufacturing processes. These weren't isolated craft techniques but systematic manufacturing capabilities applied across multiple materials and production applications. Recent analysis using modern materials science techniques has revealed that many ancient manufacturing achievements require understanding of materials properties, manufacturing processes, and precision control that rivals modern industrial capabilities. Ancient manufacturers were working with materials science principles and precision manufacturing techniques that represent sophisticated technological development. If ancient civilizations possessed such sophisticated manufacturing capabilities, what other areas of technology and applied science might they have developed to similar levels of advancement? The evidence suggests systematic technological development that applied advanced scientific knowledge to practical manufacturing and engineering problems. But advanced manufacturing represents only one aspect of the technological sophistication that ancient civilizations achieved through their systematic development of knowledge and practical applications across multiple scientific domains. Medical mastery. The medical knowledge demonstrated by ancient civilizations reveals understanding of human anatomy, surgical techniques, and pharmaceutical applications that rivals and sometimes exceeds capabilities that modern medicine has achieved only recently. Ancient medical practitioners were performing complex surgical operations, developing sophisticated pharmaceutical treatments, and applying medical knowledge that suggests advanced understanding of human physiology and disease. Ancient Egyptian medicine demonstrates surgical capabilities that require advanced understanding of anatomy, surgical techniques, and medical instruments. The Edwin Smith Papyrus, dating to 1600 BCE, contains detailed descriptions of surgical procedures including brain surgery, spinal operations, and complex wound treatments that require sophisticated medical knowledge and precision surgical techniques. The surgical procedures described in ancient Egyptian medical texts include operations on the skull, brain, and spinal column that require precision surgical techniques and advanced understanding of human anatomy. These operations involve techniques for controlling bleeding, preventing infection, and managing complex surgical procedures that require sophisticated medical knowledge and precision surgical instruments. Evidence of successful ancient surgical operations appears in mummy remains that show healed surgical wounds, bone repair operations, and medical treatments that demonstrate advanced surgical capabilities. Ancient surgeons were performing operations that required precision surgical techniques, advanced medical instruments, and sophisticated understanding of surgical recovery and wound healing. The medical instruments found in ancient Egyptian tombs include surgical tools with precision design and manufacturing that rivals modern surgical equipment. Ancient surgical instruments demonstrate sophisticated understanding of surgical requirements, precision manufacturing techniques, and medical tool design that indicates advanced medical knowledge and manufacturing capabilities. Ancient pharmaceutical knowledge demonstrates sophisticated understanding of medicinal chemistry, drug preparation, and systematic medical treatment. Ancient medical texts describe pharmaceutical preparations that include complex chemical processes, precise dosage calculations, and systematic treatment protocols that require advanced understanding of medicinal chemistry and medical practice. The pharmaceutical techniques described in ancient medical texts include chemical extraction processes, drug purification methods, and systematic preparation techniques that require sophisticated understanding of chemistry and pharmaceutical science. Ancient medical practitioners were developing pharmaceutical treatments using chemical techniques and systematic methods that represent advanced medical knowledge. Recent chemical analysis of ancient pharmaceutical preparations has revealed sophisticated understanding of medicinal chemistry and drug development. Ancient pharmaceutical preparations include active compounds, chemical processes, and systematic preparation techniques that require advanced understanding of chemistry and medical science. Ancient surgical operations demonstrate understanding of anatomy and surgical techniques that require systematic medical education and advanced surgical training. The complexity of surgical procedures described in ancient medical texts suggests medical educational systems capable of transmitting sophisticated medical knowledge and surgical techniques across generations of medical practitioners. Medical knowledge preserved in ancient texts includes systematic descriptions of human anatomy, disease diagnosis, and medical treatments that require advanced understanding of human physiology and medical science. Ancient medical practitioners were developing systematic medical knowledge that included understanding of disease processes, anatomical relationships, and medical treatments. Evidence of ancient medical specialization appears in descriptions of medical practitioners with specific expertise in surgery, pharmaceutical preparation, and diagnostic techniques. Ancient medical systems included specialized medical training, systematic medical education, and advanced medical practice that required sophisticated understanding of medical science and systematic medical knowledge. Ancient diagnostic techniques demonstrate understanding of disease processes and medical assessment that requires systematic medical knowledge and advanced diagnostic capabilities. Ancient medical texts describe diagnostic methods that include systematic patient assessment, disease classification, and medical evaluation techniques that require sophisticated medical knowledge. The diagnostic methods described in ancient medical texts include systematic approaches to medical assessment that require understanding of disease processes, anatomical relationships, and medical evaluation techniques. Ancient medical practitioners were developing diagnostic capabilities that require advanced medical knowledge and systematic medical practice. Ancient dental medicine demonstrates sophisticated understanding of dental anatomy, dental disease, and dental treatment techniques. Ancient dental operations include tooth repair, dental prosthetics, and dental treatments that require advanced understanding of dental anatomy and precision dental techniques. Evidence of ancient dental work includes dental prosthetics, tooth repair operations, and dental treatments that demonstrate sophisticated dental knowledge and precision dental techniques. Ancient dental practitioners were performing dental operations that require advanced dental knowledge and sophisticated dental instruments. Ancient veterinary medicine demonstrates systematic understanding of animal anatomy, animal disease, and veterinary treatment techniques. Ancient veterinary texts describe medical treatments for animals that require sophisticated understanding of veterinary medicine and systematic veterinary knowledge. The veterinary techniques described in ancient texts include surgical operations, pharmaceutical treatments, and diagnostic methods applied to animals that require advanced understanding of veterinary science and systematic veterinary medical knowledge. Ancient medical knowledge includes understanding of human physiology, disease processes, and medical treatments that require systematic scientific investigation and advanced medical research. Ancient medical practitioners were conducting medical investigation that included systematic observation, medical experimentation, and advanced medical knowledge development. The medical achievements documented in ancient texts represent systematic development of medical knowledge that required advanced understanding of human anatomy, disease processes, and medical treatments. Ancient medical systems included sophisticated medical education, systematic medical practice, and advanced medical knowledge that rivals modern medical capabilities in many areas. Recent analysis of ancient medical texts using modern medical knowledge has revealed that many ancient medical techniques and pharmaceutical treatments represent sophisticated understanding of medical science and effective medical practice. Ancient medical knowledge includes medical techniques and treatments that remain effective and relevant to modern medical practice. If ancient civilizations possess such sophisticated medical knowledge and surgical capabilities, what other areas of applied science and systematic investigation might they have developed to similar levels of advancement? The evidence suggests systematic scientific development that applied advanced knowledge to practical problems across multiple domains of human knowledge and capability. But medical advancement represents only one dimension of the systematic scientific investigation and knowledge development that ancient civilizations achieved across multiple areas of natural science and practical application. The systematic approach to knowledge development demonstrated by ancient civilizations suggests they possess sophisticated understanding of scientific methodology, systematic investigation, and theoretical framework development that rivals the systematic scientific investigation methods that modern science considers fundamental to scientific advancement. Ancient astronomical observations demonstrate systematic data collection, mathematical analysis, and theoretical model development that represents sophisticated application of scientific methodology. Ancient astronomers were conducting systematic observation programs that included data collection, spanning centuries, mathematical analysis of observational data, and theoretical model development that could predict astronomical phenomena with remarkable accuracy. The astronomical observations recorded in Babylonian texts include systematic data collection spanning over 700 years of continuous observation. These records demonstrate systematic methodology including controlled observation techniques, standardized data recording, and mathematical analysis methods that represent sophisticated application of scientific investigation techniques. The mathematical analysis applied to ancient astronomical data includes systematic techniques for identifying patterns, calculating astronomical periods, and developing predictive models that could forecast astronomical events. Ancient astronomers were applying mathematical techniques that included statistical analysis, mathematical modeling, and systematic error correction that represents advanced scientific methodology. Ancient medical investigation demonstrates systematic approaches to medical knowledge development that include controlled observation, systematic documentation, and empirical testing of medical treatments. Ancient medical texts describe medical investigation techniques that include systematic patient observation, controlled treatment protocols, and systematic evaluation of medical effectiveness. The medical investigation methods described in ancient texts include systematic approaches to medical research that require understanding of experimental design, controlled observation, and systematic evaluation of medical treatments. Ancient medical practitioners were conducting medical investigation using systematic methods that represent sophisticated understanding of empirical investigation and scientific methodology. Ancient engineering projects demonstrate systematic approaches to technical problem solving that include mathematical analysis, systematic testing, and iterative design improvement. Ancient engineers were applying systematic engineering methods that included mathematical modeling, systematic testing of engineering solutions, and iterative improvement of technical designs. The engineering methods applied to ancient construction projects include systematic approaches to structural analysis, materials testing, and design optimization that represent sophisticated understanding of engineering methodology and systematic technical development. Ancient engineers were developing technical solutions using Systematic methods that require advanced understanding of engineering principles and systematic problem-solving techniques. Ancient agricultural development demonstrates systematic approaches to agricultural investigation that include controlled experimentation, systematic observation of agricultural results, and systematic development of improved agricultural techniques. Ancient agricultural systems include evidence of systematic crop development, controlled agricultural experimentation, and systematic improvement of agricultural productivity. The agricultural methods developed in ancient civilizations include systematic approaches to crop selection, controlled breeding programs, and systematic evaluation of agricultural techniques that represent sophisticated understanding of systematic investigation and agricultural science methodology. Ancient mathematical development demonstrates systematic approaches to mathematical investigation that include theoretical framework development, systematic mathematical proof techniques, and systematic development of mathematical methods. Ancient mathematical texts include systematic mathematical investigation that represents sophisticated understanding of mathematical methodology, and theoretical development. The mathematical techniques developed in ancient civilizations include systematic approaches to mathematical problem solving, theoretical framework development, and mathematical proof techniques that represent advanced understanding of mathematical methodology and systematic mathematical investigation. Ancient technological development demonstrates systematic approaches to technical innovation that include iterative design improvement, systematic testing of technical solutions, and systematic development of manufacturing techniques. Ancient technological achievements represent systematic technical development that required advanced understanding of systematic innovation and technical problem-solving methodology. Evidence of systematic knowledge preservation and transmission appears in ancient educational systems that include systematic curriculum development, standardized educational techniques, and systematic preservation of advanced knowledge across generations. Ancient educational systems demonstrate sophisticated understanding of knowledge transmission and systematic educational methodology. The educational methods developed in ancient civilizations include systematic approaches to knowledge preservation, standardized educational curricula, and systematic training programs that represent advanced understanding of educational methodology and systematic knowledge transmission. Ancient investigation of natural phenomena demonstrates systematic approaches to scientific observation that include controlled observation techniques, systematic data collection, and systematic analysis of natural phenomena. Ancient scientific investigation includes evidence of systematic approaches to natural science that represent sophisticated understanding of scientific methodology. The scientific investigation conducted by ancient civilizations includes systematic observation of natural phenomena, controlled investigation techniques, and systematic development of theoretical frameworks that represent advanced understanding of scientific methodology and systematic scientific investigation. Recent analysis of ancient scientific and technical achievements using modern scientific methodology has revealed that ancient civilizations were applying systematic investigation techniques, empirical observation methods, and theoretical framework development that represents sophisticated understanding of scientific methodology and systematic investigation techniques. The systematic approaches to knowledge development demonstrated by ancient civilizations include methodological sophistication, systematic investigation techniques, and theoretical framework development that rivals modern scientific methodology in many areas of investigation and knowledge development. Ancient systematic investigation includes evidence of peer review systems, collaborative investigation techniques, and systematic verification of scientific and technical results that represent sophisticated understanding of systematic knowledge development and scientific methodology. If ancient civilizations possess sophisticated understanding of scientific methodology and systematic investigation techniques, this suggests systematic development of knowledge and theoretical frameworks across multiple domains of natural science and technical investigation that may have achieved levels of sophistication that we're only beginning to appreciate. The evidence suggests that ancient civilizations were conducting systematic scientific investigation using methodological approaches that represent advanced understanding of scientific methodology and systematic knowledge development that challenges conventional understanding of the historical development of systematic scientific investigation. But systematic scientific methodology represents only one aspect of the comprehensive technological and intellectual achievements that ancient civilizations accomplished through their advanced understanding of natural phenomena and systematic application of scientific knowledge to practical technological solutions. Lost technologies. The archaeological record contains evidence of technological achievements that appear to have been lost to subsequent civilizations, suggesting that human technological development hasn't followed the simple linear progression that our current models assume. Some ancient technologies achieved results that we struggle to replicate today, indicating technological knowledge that was subsequently lost rather than continuously improved upon. Ancient concrete technology provides one of the clearest examples of lost technological capability. Roman concrete, particularly the marine concrete used in harbor construction, demonstrates properties that modern concrete science has only recently begun to understand and struggle to replicate. Roman marine concrete actually becomes stronger over time when exposed to seawater, while modern concrete deteriorates under similar conditions. The chemical composition of Roman concrete includes volcanic ash and lime that creates a chemical reaction with seawater, producing calcium carbonate crystals that strengthen the concrete structure over centuries. This self-healing property represents sophisticated understanding of materials chemistry and long-term chemical processes that wasn't matched in construction technology until recent developments in modern materials science. Dr. Marie Jackson, who has conducted extensive research into Roman concrete using advanced materials analysis techniques, has documented how Roman concrete technology achieved durability and strength characteristics that modern concrete formulations cannot match. After 2,000 years of exposure to seawater, Roman harbor structures remain intact while modern concrete structures require replacement every 50 to 100 years. The manufacturing techniques required to produce Roman concrete include understanding of volcanic ash chemistry, lime processing, and materials mixing that represents sophisticated materials science knowledge. Roman engineers were applying materials chemistry principles and long-term chemical engineering that demonstrates advanced understanding of materials science and chemical processes. But Roman concrete represents only one example of ancient technological achievements that were subsequently lost. Damascus steel production represents another lost technology that achieved material properties that modern metallurgy continues to struggle to replicate completely. The production techniques for true Damascus steel were lost around 1750 CE, and despite extensive modern research, the complete process remains incompletely understood. Damascus steel achieved a combination of hardness, flexibility, and edge retention that represents optimal balance of material properties through metallurgical techniques that required sophisticated understanding of steel chemistry, heat treatment, and forging processes. The steel demonstrated material properties that modern materials science can partially replicate but not fully duplicate using the same methods. Recent research into Damascus steel production has revealed that the steel incorporated carbon nanotube structures that weren't formally discovered in materials science until the 1990s. Ancient steel makers were achieving nanotechnology-level materials manipulation using techniques that produced advanced material structures without modern understanding of the underlying materials science principles. Ancient optical technology demonstrates capabilities that represent lost technological knowledge in precision optical manufacturing. Ancient optical devices include mirrors, lenses, and optical systems that achieved optical properties matching modern precision optical equipment using manufacturing techniques that aren't fully understood. The Nimrod lens, dating to 750 BC, demonstrates optical properties that require precision optical grinding and polishing techniques. The lens achieves optical quality that requires understanding of optical principles and precision manufacturing techniques that represent advanced optical technology. Ancient navigation technology included sophisticated instruments and techniques that achieved navigation precision matching modern electronic navigation systems. Ancient navigation instruments demonstrate understanding of celestial mechanics, mathematical calculation, and precision instrument manufacturing that represents advanced navigation technology. Antikythera mechanism demonstrates mechanical computing technology that achieved astronomical calculation capabilities that weren't matched until the development of mechanical computers in the 18th century. This ancient Greek device includes precision gear systems, astronomical calculation capabilities, and mechanical computing functions that represent sophisticated understanding of precision mechanics and mathematical calculation. Recent analysis of the Antikythera mechanism using modern scanning technology has revealed that the device incorporated more sophisticated mechanical computing capabilities than initially understood. The mechanism includes gear systems that calculate multiple astronomical cycles simultaneously using mechanical computing techniques that require advanced understanding of gear mathematics and mechanical engineering. Ancient chemical technology demonstrates capabilities in chemical processing, pharmaceutical preparation, and materials chemistry that represent lost technological knowledge. Ancient chemical techniques achieved results in metallurgy, pharmaceutical chemistry, and materials processing that required sophisticated understanding of chemical processes and systematic chemical techniques. Evidence of ancient chemical processing includes metal purification techniques, chemical extraction processes, and pharmaceutical preparation methods that demonstrate sophisticated understanding of chemical principles and systematic chemical processing techniques. Ancient agricultural technology included sophisticated techniques for soil management, crop development, and agricultural productivity that achieved agricultural results that modern agriculture struggles to match using sustainable methods. Ancient agricultural systems achieved high productivity, soil sustainability, and agricultural efficiency using techniques that represent advanced understanding of agricultural science and soil management. And the agricultural techniques developed by ancient civilizations include sophisticated understanding of soil chemistry, crop genetics, and sustainable agricultural methods that achieved agricultural productivity while maintaining soil health over centuries of continuous cultivation. Ancient architectural technology demonstrates construction techniques and structural engineering capabilities that achieve structural results that modern construction struggles to replicate. Ancient construction techniques achieved structural stability, precision construction, and architectural sophistication using methods that require advanced understanding of structural engineering and construction technology. Recent engineering analysis of ancient construction has revealed that many ancient building techniques achieved structural efficiency and construction precision that modern construction methods struggle to match. Ancient builders were applying structural engineering principles and construction techniques that demonstrate sophisticated understanding of engineering and construction technology. Lost ancient technologies include systematic knowledge and practical techniques that achieve technological results across multiple domains of technical capability. The technological achievements documented in ancient sites and artifacts represent systematic technological development that achieved advanced capabilities that were subsequently lost, rather than continuously improved upon. The pattern of lost ancient technologies suggests that technological development doesn't necessarily follow linear progression, but may include technological achievements that can be lost when the knowledge systems and cultural frameworks that support them are disrupted or abandoned. If ancient civilizations achieved technological capabilities that were subsequently lost, this suggests that technological development may be more vulnerable to disruption and loss than our current models assume, and that human technological capability may have achieved higher levels in the past than our current understanding of technological development recognizes. But lost technologies represent only one aspect of the evidence suggesting that ancient civilizations achieved comprehensive technological and scientific capabilities that challenges our current understanding of human technological development and the relationship between past and present technological achievement. The conventional narrative of human civilization assumes a steady progression from primitive hunter-gatherers to increasingly sophisticated agricultural and technological societies. But this comfortable timeline faces serious challenges from archaeological evidence that suggests much older dates for advanced human achievements and technological capabilities that don't fit anywhere in our accepted chronology of human development. The problem isn't just isolated anomalies or questionable dating techniques. It has systematic evidence from multiple lines of investigation that consistently points toward much greater antiquity for advanced human capabilities than our current models can accommodate. When geological evidence, astronomical alignments, and technological analysis all point toward the same conclusions, the cumulative weight of evidence becomes difficult to dismiss. Göbekli Tepe in Turkey provides one of the most dramatic examples of archaeological evidence that challenges conventional timelines. This massive stone complex predates agriculture, metallurgy, and written language by thousands of years according to standard archaeological timelines. Yet the site demonstrates architectural sophistication, astronomical knowledge, and engineering capabilities that require advanced planning, mathematical knowledge, and organizational systems. The carbon dating at Göbekli Tepe consistently places construction beginning around 9600 BC, with evidence of continuous development over thousands of years. But the sophistication of construction, the precision of astronomical alignments, and the complexity of symbolic representation suggest capabilities that don't appear elsewhere in the archaeological record for another 6,000 years. Dr. Klaus Schmidt, the archaeologist who led excavations at Göbekli Tepe until his death in 2014, repeatedly stated that the site forced a complete reconsideration of the timeline of human cultural development. The organizational capabilities required to construct Göbekli Tepe suggest complex social systems, specialized labor, and technological knowledge that supposedly wouldn't develop until civilizations achieved agricultural surplus and urban development. But Göbekli Tepe represents only the most dramatic example of archaeological sites that challenge conventional chronology. Underwater archaeological discoveries off the coasts of India, Japan, and the Mediterranean include structural remains that would have been above sea level only during periods of much lower ocean levels and conditions that haven't existed for over 10,000 years. The underwater structures near Dwarka, India, include construction techniques and architectural features that demonstrate sophisticated engineering and planning. The structures show evidence of advanced urban planning, sophisticated construction techniques, and architectural sophistication that requires advanced technological capabilities. Yet their underwater location indicates construction dates that predate conventional timelines for advanced civilization in the region by thousands of years. Similar underwater archaeological sites off the coast of Japan include the Yamaguni Monument, a massive stone structure with architectural features including steps, platforms, and geometric arrangements that require sophisticated planning and construction capabilities. Geological analysis indicates that the structure would have been above sea level approximately 12,000 years ago, placing its construction well before conventional dates for advanced construction techniques in the region. The geological evidence for much older advanced construction becomes even more compelling when examined through the lens of climate change and sea level variations. During the last ice age, sea levels were 400 feet lower than current levels, exposing vast coastal areas that are now underwater. These areas would have provided optimal locations for early civilizations of flat, fertile, coastal plains with access to both marine and terrestrial resources. If advanced civilizations developed on these now submerged coastal plains, the archaeological evidence would be underwater, accessible only through marine archaeology techniques that have been systematically applied only recently. The archaeological record may be missing thousands of years of human development that occurred in locations now buried under hundreds of feet of seawater.